6 August 1945, 8:30 in the morning. Over the city of Hiroshima, a single American B-29 bomber called Enola Gay banks away, its crew shielding their eyes behind dark glasses. Below them, a city of 350,000 people is going about an ordinary Monday. Trams are running. Children are walking to school. A woman hangs washing on a line behind her house near the Aioi Bridge, unaware that this crossing has just become the aiming point for the most destructive weapon ever built. 43 seconds after release, at a height of roughly 600 meters above the city, the bomb detonates. Witnesses more than 3 kilometers away describe a flash brighter than the sun, followed by a wind that flattens buildings as though they were made of paper. A pilot in a following aircraft later says the mushroom cloud rose faster than his instruments could track. Within a single moment, an entire city has been transformed into ash, rubble, and silence. 3 days later, on the 9th of August, it happens again over Nagasaki. Within a week, Japan has announced its surrender, and the Second World War, the deadliest conflict in human history, is over. To understand how the world arrived at that Monday morning, we have to go back 6 years, to a handful of physicists scribbling calculations on university blackboards, half convinced that what they were describing was theoretically impossible to build in time to matter. What follows is the story of how an idea moved from academic curiosity to operational reality in less time than it takes to build a modern motorway, and how that single decision continues to shape international relations more than 8 decades later. This is a story about physics, certainly, but it is really a story about what happens when a nation decides that a weapon must exist, whatever the cost, and races against an enemy it fears is thinking exactly the same thing. By 1939, the world had already spent a generation refining the machinery of mass killing. The First World War had introduced poison gas and machine guns capable of cutting down thousands of men in an afternoon. The Second World War, barely underway, was already demonstrating that aerial bombing could reduce entire cities to rubble using nothing more exotic than incendiaries and high explosive, dropped by the 100 over Coventry, Rotterdam, and later Hamburg and Tokyo. The technology of destruction, in other words, was already terrifyingly mature. What it lacked was efficiency. A conventional bombing raid on a city the size of Tokyo, carried out in March 1945, required over 300 aircraft, each carrying several tons of incendiary bombs, to kill perhaps 100,000 people and destroy 16 square miles of the city in a single night. It was an enormous undertaking. Months of planning, thousands of aircrew placed at risk, and an entire industrial base dedicated to producing the bombs and the bombers that carried them. And still, city after city had to be attacked in turn, because no single raid could end a war on its own. The physicists who began theorizing about nuclear fission in the late 1930s understood something that the military planners had not yet grasped, that the energy locked inside the atomic nucleus was, weight for weight, millions of times greater than anything achievable through chemical explosives. A lump of the right material, no larger than a grapefruit, contained, in theory, the destructive potential of thousands of tons of conventional explosive. The trouble was that nobody had the faintest idea, in 1939, whether this could actually be engineered into a usable weapon, or whether it would remain a mathematical curiosity forever locked inside academic journals. Then came a letter. In August 1939, Albert Einstein, at the urging of fellow physicists Leo Szilard, Eugene Wigner, and Edward Teller, wrote to President Franklin Roosevelt warning that Nazi Germany might be pursuing exactly this kind of weapon. The fear was not abstract. German scientists had, after all, been the ones to first split the uranium atom in Berlin, in December 1938. If Germany built such a weapon first, the balance of the war, and quite possibly the future of Europe, would tilt in ways nobody wanted to contemplate. The race, in the minds of the men who mattered, was already underway, whether or not Germany was actually running it with any seriousness. That uncertainty, more than any confirmed intelligence, is what pushed the United States towards the most expensive weapons program in human history. What became known as the Manhattan Project began in earnest in 1942, placed under the direction of Major General Leslie Groves, an Army engineer who had recently overseen construction of the Pentagon, and the physicist Robert Oppenheimer, who was given command of the project's secret laboratory. The scale of what followed is difficult to overstate. Roughly 130,000 people were eventually employed across the project, most of them with no idea what they were actually building. 3 vast facilities were constructed almost overnight: a uranium enrichment plant at Oak Ridge in Tennessee, a plutonium production complex at Hanford in Washington State, and a design and assembly laboratory built from scratch on a remote mesa at Los Alamos, New Mexico, chosen partly because Oppenheimer had once holidayed nearby and knew the isolation would keep the work concealed. The fundamental challenge facing the scientists at Los Alamos was straightforward to describe and monstrously difficult to solve. Certain heavy elements, uranium and plutonium among them, can be made to split their atomic nuclei apart in a self-sustaining chain reaction, releasing colossal amounts of energy in a fraction of a second, provided enough of the material is brought together quickly enough and provided that material is of a rare, highly refined form. Producing that material in usable quantities required industrial process that had never before existed at scale, consuming a significant fraction of the electrical power generated in the entire United States at the time. Oak Ridge alone drew more electricity than the whole of New York City. 2 distinct weapon designs eventually emerged from this effort, built around 2 different fissile materials, uranium and plutonium, each requiring an entirely different engineering approach to bring the material together at the necessary speed and density. So confident were the scientists in the simpler of the 2 designs that it was never even tested before use in combat. The other design was considered sufficiently uncertain that it demanded a full trial, carried out in the New Mexico desert on July 16, 1945, near a site the project's leaders had, with a certain grim poetry, codenamed Trinity. Observers stationed many kilometers away described a light brighter than several suns, felt heat on their faces from that distance, and watched a fireball climb into a mushroom-shaped cloud that reached over 12 kilometers into the sky. Oppenheimer himself later recalled a line from Hindu scripture crossing his mind in that instant, that he had become death, the destroyer of worlds. The bombs that followed, nicknamed Little Boy and Fat Man for their distinct shapes, weighed in the region of 4 to 4.5 tons each, roughly the mass of a fully loaded delivery lorry, and had to be specially adapted to fit inside modified B-29 bombers, the only aircraft in the American arsenal large enough to carry them. Each represented years of theoretical work, industrial investment on a scale normally reserved for entire wars, and a level of secrecy so absolute that most of the men who flew the missions did not know precisely what they were carrying until after the fact. By the summer of 1945, Germany had already surrendered. Its own nuclear program revealed to have never come remotely close to a workable weapon. The war in the Pacific, however, continued, with American planners bracing for an invasion of the Japanese home islands that some estimates suggested could cost hundreds of thousands of Allied casualties and far higher numbers among Japanese defenders and civilians. It was against this backdrop, weighing an already devastating conventional bombing campaign against the terrifying uncertainty of invasion, that the decision was made to use the new weapon. If you are finding this interesting so far, a quick subscribe helps more than you know, and it costs you nothing. Hiroshima was chosen partly because it had, by chance or design, escaped serious bombing until that point, meaning the destructive effect of a single weapon could be measured with unusual clarity against an otherwise intact city. The bomb detonated above the city with a force estimated at around 15,000 tons of TNT equivalent, a figure that becomes almost meaningless until you consider that it was delivered not by a fleet of 300 bombers over an entire night, but by a single aircraft in a matter of seconds. Somewhere between 70 and 80,000 people are thought to have died immediately or within the following weeks, with tens of thousands more succumbing later to burns, radiation sickness, and injury. Exact figures remain disputed to this day, partly because so many records and so many of the people who might have provided them were lost in the same instant. Nagasaki followed on the 9th of August, the bomb originally intended for another city entirely, diverted at the last moment due to cloud cover. Hillier terrain around Nagasaki actually confined the blast somewhat compared to Hiroshima's flat expanse, yet the death toll still likely exceeded 40,000 in the immediate aftermath, rising substantially in the months that followed. Survivors, known in Japan as hibakusha, described a light like a photograph. Negative burned instantly into whatever surface it touched. Shadows of people and objects scorched permanently onto walls and pavements where the individuals themselves had simply ceased to exist. The psychological impact on Japan's leadership arguably mattered as much as the physical destruction. Combined with the Soviet Union's declaration of war against Japan on the 8th of August, the bombings presented an argument that conventional bombing, however devastating, had failed to make. That the war could now be ended, not city by city over years, but potentially overnight, with a single aircraft and a single weapon. On August 15th, Emperor Hirohito addressed the Japanese people by radio for the first time in history, announcing surrender in language so formal that many listeners struggled to grasp its actual meaning. What they understood clearly enough was that the war, at extraordinary cost, was finally over. It is worth pausing here to consider what Germany and Japan had themselves attempted. German physicists, working under wartime conditions with dwindling resources and, crucially, without ever securing the same scale of state investment or industrial mobilization as the Americans, never progressed beyond small experimental reactors. Historians continue to debate whether this reflected a genuine technical dead end, a lack of political urgency, or simply a set of scientists quietly reluctant to hand Adolf Hitler such a weapon. Japan's own wartime nuclear research, spread across a small number of underfunded university laboratories, never advanced beyond preliminary theoretical work. The Soviet Union, meanwhile, was running its own program throughout this period, aided considerably by espionage that had penetrated the Manhattan Project itself, and would successfully test its own weapon by 1949, a mere 4 years after Hiroshima, far sooner than American planners had predicted or hoped. What set the American effort apart was not necessarily superior scientific insight, since the underlying physics was understood, in broad terms, by researchers in several countries. What set it apart was the willingness to commit an almost unimaginable quantity of money, industrial capacity, and skilled labor to a project whose success was, at the outset, genuinely uncertain. It was, in the truest sense, a wager that the theoretical promise of nuclear fission could be turned into a working weapon before the war that justified building it had ended. The legacy of that August remains almost impossible to summarize neatly because it operates on so many levels simultaneously. In purely military terms, it is credited by many historians, though not all, with hastening the end of the Pacific War and avoiding an invasion that would likely have cost immense numbers of lives on both sides. In human terms, it inflicted suffering on a scale that survivors, doctors, and later generations of researchers are still working to fully document, from the immediate blast injuries to the long-term effects of radiation exposure that persisted for decades afterward. In strategic terms, it opened a new chapter in human history entirely, one in which a handful of nations acquired the theoretical capacity to end civilization as we know it, a fact that has shaped every major geopolitical decision made since. The weapons themselves and the physics that made them possible quickly proliferated. The Soviet Union tested its own device in 1949. Britain followed in 1952, France in 1960, China in 1964. Each new test compressed the timeline further as design principles once demonstrated to work became progressively easier to replicate. What began as the most expensive and secretive engineering project ever undertaken had, within 20 years, become a capability held by half a dozen governments, and the tense standoff that followed, often described as the Cold War's defining feature, shaped diplomacy, culture, and military planning for the following 4 decades. Visitors to Hiroshima today can walk through the Peace Memorial Park, built around the skeletal ruins of a building that somehow remained partially standing directly beneath the blast, preserved deliberately as it was found. The Hiroshima Peace Memorial Museum holds artifacts recovered from the ruins, twisted metal, melted glass, a child's tricycle, that communicate the human scale of that morning far more effectively than any statistic. Nagasaki maintains its own museum and memorial, situated close to the site of the second detonation, offering testimony collected directly from hibakusha over the decades since. So what, in the end, was actually achieved on those 2 days in August 1945? A war that had already claimed an estimated 70 million lives worldwide came to its final, definitive close within days. A weapon that had existed only as theoretical physics 6 years earlier had become an operational reality, deployed twice, and never used in anger again in the 8 decades since, a record that owes as much to deterrence and diplomacy as it does to restraint alone. 2 cities, functioning urban centers with markets, schools, hospitals, and tens of thousands of ordinary lives, were destroyed within the space of a single morning each, and the survivors carried the physical and psychological consequences for the remainder of their lives. The scientists who built the weapon understood almost immediately what they had unleashed. Several of the very physicists who had pushed hardest for its development spent the remainder of their careers campaigning for international controls on nuclear weapons, haunted by the speed with which theory had become atrocity. Robert Oppenheimer himself would later oppose the development of the far more powerful hydrogen bomb, and would spend his final years watched with suspicion by the same government he had once served with such singular focus. 6 August 1945 did not simply end a war. It opened a door that has never been closed again, and every government on Earth has had to decide, in the decades since, how to live in a world where that door remains open. The bomb that fell on Hiroshima weighed roughly 4 tons. Its consequences have weighed on human civilization ever since, and they show no sign of growing lighter.